Is time travel possible in our universe? Have you ever wished you could glimpse the future, or perhaps right or wrong from the past? The idea of time travel, jumping through the fourth dimension, has captivated humanity for centuries. But is it just the stuff of science fiction blockbusters, or could it genuinely be a reality in our universe? Today, we're diving deep into the fascinating, and sometimes paradoxical, world of time travel. The astounding truth is, we are all time travelers, constantly moving forward at a rate of 1 second per second. But what if we could speed up or slow down that journey? According to Albert Einstein's theories of relativity, time isn't a constant, universal ticker. It's relative, and it can be affected. The key concept here is time dilation. Einstein's special theory of relativity, published in 1905, tells us that the faster you move through space, the slower you experience time relative to someone stationary. This isn't just theory, it's a proven fact. One of the most famous early experiments demonstrating time dilation involved atomic clocks. In 1971, the Havlicek experiment flew highly precise cesium beam atomic clocks around the world on commercial airplanes, one eastward and one westward. When they returned, they were compared to a stationary atomic clock at the U.S. Naval Observatory. The clocks on the planes were indeed slightly behind or ahead, exactly as predicted by relativity, by mere nanoseconds, but undeniably, this minuscule, immeasurable difference confirmed that motion affects the passage of time. This effect is even crucial for our everyday technology. To GPS satellites orbiting Earth at an altitude of about 20,200 kilometers (12,550 miles) move at speeds of approximately 14,000 kilometers per hour, 8,700 miles per hour relative to the ground. If their internal clocks weren't constantly adjusted for both special and general relativistic effects, they would drift by roughly 38 microseconds per day. This seemingly tiny error would quickly accumulate, causing GPS systems to become inaccurate by several kilometers per day, making navigation impossible. This constant calibration is a testament to the reality of time dilation. It's not just speed that can warp time. Einstein's general theory of relativity, published in 1915, introduces another profound time-bending factor: gravity. The stronger the gravitational field, the slower time passes for observers within that field, relative to those in weaker fields. This means time moves infinitesimally slower at sea level, where gravity is slightly stronger than it does on top of a very tall mountain. Again, this has been experimentally verified with incredibly precise atomic clocks. For example, experiments at the National Institute of Standards and Technology (NIST) had shown that an atomic clock placed just 30 centimeters, about 1 foot higher than another, will tick ever so slightly faster. We're talking about a difference of nanoseconds, but it's a measurable and consistent effect. So, standing on a massive planet, or even more dramatically, near a neutron star or a black hole, would genuinely slow down your personal clock relative to someone far away. So, time travel to the future is undeniably possible and even an everyday reality for astronauts. Astronauts on the International Space Station (ISS), orbiting at speeds of 28,000 kilometers per hour, 17,500 miles per hour, experience time slightly slower than us on Earth. While the effect is minuscule, about 0.01 seconds over 6 months, it means that ISS astronauts are technically traveling into Earth's future, albeit by a tiny fraction of a second. If you could travel close to the speed of light for an extended period, or spend time in an extremely strong gravitational field, you would age slower than people on Earth. When you returned, you would have traveled significantly into their future. Consider the famous twin paradox. If one twin embarked on a round trip to a distant star at near light speed, while the other remained on Earth, the traveling twin would return to find their earthbound sibling much older. For a journey to a star 20 light-years away at 99.999% the speed of light, the space twin might only age a few months, while the Earth twin would have aged over 40 years. The biggest challenge for significant future time travel is the immense energy required to accelerate a spacecraft to such relativistic speeds. We're talking about energy equivalent to the output of entire stars. The most extreme example of gravitational time dilation would be near a black hole. As you approach a black hole's event horizon, the point of no return, the gravitational pull becomes so incredibly intense that time would appear to slow to an almost complete stop for an outside observer. For someone falling into it, however, they would continue to experience time normally, accelerating towards the singularity in what would feel like a finite amount of their own personal time. This is a one-way trip, of course. Once past the event horizon, nothing, not even light, can escape. So, while a black hole could be a powerful future time machine for the outside universe, it's not a round-trip ticket. Now, for the big question, can we travel to the past? This is where things get truly speculative and fraught with paradoxes. While the mathematics of general relativity does allow for some exotic spacetime geometries, known as closed time-like curve CTCs, that could theoretically enable backward time travel, we have no empirical evidence or practical means to achieve it. These theoretical constructs often involve highly improbable conditions or materials that may not exist in our universe. One popular theoretical concept for backward time travel is a wormhole, also known as an Einstein-Rosen bridge. Imagine folding a piece of paper and punching a hole through it, connecting to distant points directly. A wormhole would be a shortcut through spacetime, potentially connecting not just different locations, but different points in time. Theoretically, if one end of a traversable wormhole one you could actually pass through were moved at near light speed, or placed in a strong gravitational field, time dilation would occur, creating a time difference between its two mouths. Stepping through could then, in theory, lead to the past or future. However, creating and stabilizing such a wormhole would require immense amounts of exotic matter with negative energy density. This is matter that would behave repulsively, essentially propping open the wormhole, and we have no idea how to produce it or even if it genuinely exists outside of mathematical theory. Furthermore, even if such matter exists, containing and manipulating it on a cosmic scale is beyond our wildest current technological dreams. Beyond wormholes, other highly theoretical concepts for manipulating spacetime to allow for past travel include rotating black holes, like Kerr black holes, which theoretically could allow for CTCs, and even cosmic strings. Cosmic strings are hypothetical one-dimensional topological defects in spacetime, incredibly dense and thought to be remnants from the early universe. Some theoretical models suggest that two cosmic strings whipping past each other at high speeds could, in principle, bend spacetime sufficiently to allow for backward time travel. However, like wormholes, these ideas require extreme conditions and materials that are currently purely hypothetical. The biggest roadblock to past time travel isn't just technology, it's causality. If you could go back in time and change the past, it could lead to impossible paradoxes. The most famous is the grandfather paradox. What if you went back in time and prevented your grandparents from meeting, thus preventing your own birth? If you were never born, you couldn't have gone back in time to stop them, meaning they would have met, and you would have been born. A logical contradiction that breaks the fabric of cause and effect. Another mind-bending paradox is the bootstrap paradox, also known as an ontological paradox. This occurs when an object or piece of information travels back in time and becomes the cause of its own existence, with no discernible origin. Imagine a scientist from the future goes back in time and gives Isaac Newton a copy of his own published Principia Mathematica. Newton then uses this book to develop his theories and publish his work, which eventually ends up in the hands of the future scientist. Where did the original knowledge of calculus and gravity come from? It would have no true beginning, caught in an infinite, self-sustaining loop. Physicists have proposed ways around these paradoxes, though they remain hotly debated. One idea is the many worlds interpretation of quantum mechanics, suggesting that every time a choice is made or an event occurs, the universe splits into multiple parallel universes. So, if you went back and killed your grandfather, you would simply create a new, branch timeline where you were never born, while your original timeline remains untouched. Another concept is the Novikov self-consistency principle, which proposes that the laws of physics would simply prevent any paradox from occurring. No matter how hard you tried to change the past, some event would always conspire to prevent it, ensuring consistency. You might try to prevent an event, only to inadvertently cause it, or some unforeseen accident prevents your intervention. Despite the tantalizing theories and the captivating allure of science fiction, current scientific consensus is that time travel to the past remains highly improbable, if not outright impossible, given our current understanding of physics, the immense energy requirements, the need for exotic matter, and the unresolved paradoxes present formidable barriers. Stephen Hawking famously held a party for time travelers, but sent out the invitations after the party. No one showed up, which he cited as empirical evidence against backward time travel. While telescopes allow us to see into the past by observing light from distant galaxies that took billions of years to reach us, actual physical travel to previous moments in time is a different beast entirely. So, while we are all perpetually time traveling into the future at varying rates, thanks to Einstein's profound insights into relativity, journeying to the past remains a captivating dream of science fiction. The universe, in its elegant complexity, seems to guard its past with an unbreakable lock, that the pursuit of understanding time's mysteries continues to push the boundaries of human knowledge and imagination. Who knows what future discoveries might reveal, or what new dimensions of time we might one day comprehend. Thanks for watching, and keep questioning the fabric of reality.